Hey everyone, welcome into lecture number 19 of linear algebra. This lecture is on the singular value decomposition of a matrix. So following the text, we are going to make a couple of assumptions here at the outset. I'll outline the problem and then we'll go through a derivation of how to find the singular value decomposition and do a couple examples. So for the setup of this method here, this decomposition, let's let A be an n by n matrix. And in general, the singular value decomposition works for any size matrix, but following the text, let's say for convenience, and this is just for convenience of the computations that we're going to outline soon here, let's assume that m is greater than or equal to n. So it'll be an exercise at the end of this lecture to think about what changes when m is less than n, and it's not going to be too much. So in general, all of the ideas that we discuss in this lecture will still hold when m is less than n. So the goal here is that we want to decompose A. So we want to find a factorization of A. So let me write this out. We want to find a factorization of the matrix A that looks as follows. So our A is going to be, when we're done with this method here, it's going to be equal to a matrix U times a matrix sigma times a matrix V transpose. Okay, and so the idea here, we need to say what these matrices are, right? So where U and V are both going to be orthogonal matrices of appropriate dimensions. So I'm going to write out what the dimensions are, but because of where they lie in relation to the sigma and because of the dimensions of A, U has to be an m by m orthogonal matrix. So U is in Rm by m, and V is going to have to be an n by n orthogonal matrix. So the orthogonal is what we're striving for, right? But just for this multiplication to work out properly, if we want these to be square matrices, then that's going to have to be the dimensions of them. So these are going to be our orthogonal. So those are going to be orthogonal matrices. And then the matrix sigma is going to be, if m is not equal to n, then it will not be a square matrix. So sigma is going to be in Rm by n. So that's the way it has to work for this multiplication to give us the right dimension, right? But sigma is going to be as close to a diagonal matrix as you can get with a non-square matrix, and it's going to have the following entries here. So I'll write it this way. This matrix sigma is going to be of the form. So it's going to be very close to being diagonal, right? And so if it's a square, if the dimensions are the same here, if we're working with a square matrix, then it will be a diagonal matrix here. And the entries are going to be sigma 1, sigma 2, sigma 3, etc. to sigma n along the diagonal. And this is one of the places where we've made the assumption that m is greater than or equal to n. And so I'm going to extend my brackets here because now I've reached the final column and everything else is going to be zeros. Okay, now the sigmas themselves are going to obey some relationships here. So the sigma, this is supposed to be along some kind of, as close to the diagonal as you can get here. But the sigmas, we want to make sure that they obey the following. So we want them to start with the largest one and then decrease. And all of these sigmas are going to be non-negative. So sigma 1 is going to be greater than or equal to sigma 2, greater than or equal to sigma 3, etc., all the way down to sigma n. And all of these are going to be greater than or equal to 0. Okay, so this is our goal. We want to find this kind of a factorization of our matrix. Now, the name of the factorization or the decomposition is called the singular value decomposition. And this matrix here is called the matrix of singular values, okay, the sigma matrix. And the values here, these positive values, sigma I in this case, those are going to be the singular values of the matrix A. So the sigmas are the singular values. This is where the name comes from of the decomposition. The singular values of A, and this factorization is the SVD, or singular value decomposition. All right. So the reason that this is going to be important is because now we're going to have two orthogonal matrices, U and V, right? We know orthogonal means that the transpose is the inverse, right? So U times U transpose or U transpose times U is equal to identity. So those are going to end up being, we'll see exactly where those two matrices come from, but the matrices U and V are going to be orthogonal, and so in some sense this matrix sigma is going to encode quite a bit about how the matrix A actually behaves, okay? So, and really it's going to have a lot to do with the rank of the matrix, and this is a very useful computational tool. The SVD, the singular value decomposition, is going to be a very useful computational tool for people who are doing numerical calculations with very, very large matrices. They frequently will look at the singular values and then determine how close a matrix is to being rank deficient. So in other words, if these singular values get very small, then your matrix is close to losing rank, right? And when you're working in numerical calculations, frequently you want to be careful of those kind of issues where you have a matrix that's close to losing rank, where one of these values is 0 or very, very close to 0. So I stopped writing here, but the factorization is called the singular value decomposition, which we'll call the SVD from now on. So the singular value decomposition, or SVD. And in many programming languages or systems, for example, like MATLAB, SageMath, which is based on Python, but SageMath, probably in Mathematica, SVD is actually the command that you call. You call SVD of your matrix, and it will give you the singular value decomposition. But we want to know exactly what it's doing in this class, right? So for the next step here, the next item, let's write out a theorem, and we will then, the proof of this theorem will be the derivation of the method for computing the singular value decomposition, which is really what we want to know here. How do we actually compute the SVD of a matrix? So here's the theorem. Once I write this, you should understand why this is a very important theorem. But if A is an m by n matrix, this is the theorem, then A has a singular value decomposition, or I've just abbreviated it, it has an SVD. So in this case, I'm saying it is possible to find the matrices U, V, and sigma to write your given matrix as a product. A equals U times sigma times V transpose. So this is an existence theorem. It says that, okay, I've just laid out this process of what we want to find, and this theorem is going to tell us that it is not going to be a waste of our time to try to find such a decomposition, right? So the singular value decomposition of every matrix exists, and therefore we can find it, right? We can try to find it. So here's the proof. This is going to be a very long proof, and the point of the proof is partially to prove the theorem, but more importantly, the reason that we're going to go through all the details, or at least most of the details, is because it's going to tell us, the proof is going to tell us how to compute the singular value decomposition if we're given a matrix. Okay? So I am going to start by saying, let's consider, so we've got this matrix A, right? So let's first start by considering the matrix A transpose A. So this matrix A transpose A is symmetric, right? This is a symmetric matrix. And therefore, I'm going to make a claim here that if you don't believe, you should go back and verify. There was an exercise about this in the chapter on diagonalization, so which was our last lecture, actually. But this claim then is the following. Therefore, its eigenvalues are all real, because it's symmetric, so that part's easy to verify, and we've done an exercise on that, hopefully. But the eigenvalues are all real, and it has an orthogonal diagonalizing matrix. So it can be diagonalized with an orthogonal matrix, right? So this is important. So it has an orthogonal diagonalizing matrix, and this is going to actually be the matrix V. Whoops, diagonalizing matrix V. All right, so there's our matrix V that we're going to get. So we're going to take the matrix A make A transpose A, the symmetric n by n matrix in this case, and then find its diagonalizing matrix. Remember, if you need to, go back and review the lecture on diagonalization and diagonalizing matrices. But the diagonalizing matrix is the matrix which shows up as, we wrote it as X in that lecture, right? So X d X inverse is equal to A. In this case, we're going to use V. We're going to call it V. This is going to be an orthogonal diagonalizing matrix. All right, and there is one more claim that I'll make right here. So furthermore, all of the eigenvalues of A transpose A are non-negative. So again, if you don't believe these claims, then you should pause the video, go back, look through the lecture on diagonalizing matrices and maybe in eigenvalues, go through some of the old exercises that you've done and make sure that you believe these claims, that the eigenvalues are real, that the matrix is diagonalizable, and that the diagonalizing matrix is orthogonal. Okay, so that's a big claim here. And then that the eigenvalues of A transpose A are not only real, but they're non-negative. So take a moment and verify those claims. The matrix V here, though, once you've done that verification, this matrix V is the one we want. So that's why I've called it V here. But so there we go. So we've got one part of our factorization now. We've got our matrix V. It's going to be the diagonalizing matrix of A transpose A. So at this point, the next thing that we'll find are the singular values. Remember, those are the entries in this matrix sigma, the kind of diagonal entries, even though this is not a square matrix necessarily, but the diagonal entries. So we want to compute these. So let's say the following. So let's let now lambda be an eigenvalue of this matrix A transpose A. So we've already said now that that's a non-negative number, right? But we're actually going to verify that now. And let's let X be a corresponding eigenvector to this lambda. So that means that X it's at least related to a column of V, right? A column of V. The columns of V are unit, right? Because it's an orthogonal matrix, so they form an orthonormal basis for the column space of V. So the X is maybe not exactly one of those, but it's related, right? So it's a constant multiple of one of those, if nothing else. So what we can do then is we can compute the following. So look at this computation. If we take the norm, or the length, of A times X, so we take just the matrix A, not A transpose A. Remember, lambda is an eigenvalue of A transpose A, but we're going to just take A times X, okay, the matrix A that we're concerned with from the outset, and take its norm. Well, remember how this works. So one of the calculations we have for computing the length of this vector is that this is going to be then A times X transpose times A times X. All right. So this is then going to be X transpose A times X. This whole term right here, this is now A transpose A times its eigenvector. So this is just going to be lambda times X. We can replace it by constant lambda times X, right? And so this one can be written, and then the lambda can come out, but I'll write it in two steps. So X transpose lambda X. All right, and then it comes out again. So lambda X transpose X. And so then this is lambda times the norm of X. All right, the length of X. So what we find then is that we can, and by the way, X is an eigenvector. It was assumed to be an eigenvector, so X is not the zero vector, right? And so what we can do then is divide through by this norm of X. So the way I wrote this, X is not the zero vector, which means that its length is not zero, right? Because it was assumed to be an eigenvector, and eigenvectors have to be non-zero vectors. And so what we find then our lambda is equal to the norm of A times X divided by the norm of X. All right? And this has to be, these are two positive numbers. Well, this is non-negative and this is positive, right? So this has to be greater than or equal to 0. So there we go. So that proves that our eigenvalues are non-negative for this matrix A transpose A. And from here, we can use this idea to define our singular values now. So now that we know that these values are non-negative, these lambdas are non-negative, we can use them to define the singular values of the matrix A. To do so, though, remember we also had this criteria up here that the sigmas should be ordered in such a way that they're decreasing, right? As you move through the columns of sigma, the values of the lowercase sigmas are decreasing. And so to do that, we want to order the columns of V. So we assume, I'll say in this case, but if it's not true, we'll rearrange, right? And we'll remake our matrix V. But we assume that the columns now of V are arranged so that their corresponding eigenvalues are decreasing. So remember, each column vector of V is an eigenvector of A transpose A. So the corresponding eigenvalues are decreasing. Okay, and so what that means then is we're going to get this property, right? So lambda 1, which will correspond to column 1 of the eigenvector matrix, right, V. So lambda 1 will be greater than or equal to lambda 2, greater than or equal to lambda 3, etc., all the way down to lambda n, and these are all non-negative. They could be 0, right? And if any of them are equal, the ordering doesn't matter, so that's okay. And then what we do is we define our singular values to be the square roots of these. So now we define the sigma I to be the square root of lambda I. So these are our singular values. So the singular values are the square roots of the eigenvalues of the matrix A transpose A. All right, so at this point now, once we have done this, then we now have built, remember how the matrix sigma works. The matrix sigma is basically diagonal. So once we know the values of those entries, then the matrix is known, right? We know the matrix. And as long as we have our V ordered as we just described right here, right? So as long as we have our columns of V ordered in the proper ordering, then we know the matrix V as well. And so if we know V, we know V transpose. So we've got 2/3 of our singular value decomposition taken care of. All right? So the last thing that we need to consider is how do we find the matrix U? That's got to be an orthogonal matrix, and that one has to be M by M, right? So to do that, we are going to continue on with this process, but we need to say a couple things here first. So let's let now R equal the rank of the matrix A. So remember, the rank of the matrix A can be defined many different ways. It's the dimension of the column space, the dimension of the row space, those are equal. It's also the number of non-zero eigenvalues, right? And we have a result that the rank of A has to be the same as the rank of A transpose A, right? So we also know then that the rank of A transpose A is equal to R. And this then tells us, right? So since A transpose A is symmetric and it has rank R, then it has R non-zero eigenvalues. So A transpose A, so in other words, the lambdas, right? So it has R non-zero eigenvalues. Okay, so what we learned then, well, we can say this, right? So what we can say then, we can basically divide up the eigenvalues. So if we say R maybe is less than n in this case, and then what we can do is write the following. So our lambda 1 will be greater than or equal to lambda 2. We've already got these ordered this way, right? All greater than or equal to lambda R greater than 0. So those are the non-zero eigenvalues. And the rest of them, lambda R plus 1 equals lambda R plus 2, all the way up through lambda n, these are all equal to 0, right? The rest of the eigenvalues will be equal to 0. And the singular values will be then decomposed, or they'll obey the same identities, right? So not identities, but they'll have the same properties, because when you take the square root on positive values here is not going to change the ordering, right? So that we get the similar ordering of our singular values. So sigma 1 is going to be greater than or equal to sigma 2 through sigma r. Those are all positive, and the rest of the sigmas, the rest of the singular values, are going to be equal to 0, right? So at this point, what we do is we can partition the two matrices that we've already made. So we can partition those, okay? We do the following. We can partition V into the following: V1, V2. So we write this as a partition matrix in the following sense, right, where these V's are equal to the following. So V1 is going to be the first R columns of our matrix. We're not changing the matrix at all, we're just partitioning it. So the first R columns of our matrix, and V2 is going to be the rest of it. So these are going to correspond to the 0 singular values, right, or the 0 eigenvalues of A transpose A. So we just partition this in terms of the vectors that correspond to the non-zero eigenvalues, and then the ones that correspond to the 0 eigenvalues. And so that'll be the rest of them, right? We can do the same thing with the matrix sigma. So similarly, we have the following. So sigma can be decomposed. This time we want to make this into a block matrix. So we'll write it as sigma 1, 0, 0, 0. Remember, this matrix has a very simple form anyway, right? But now what we can say for sure is that sigma 1 is going to be a square diagonal matrix. So sigma 1 is going to be the matrix of non-zero singular values. So sigma 1, sigma 2 through sigma r. This is a diagonal matrix, right, in R by R. So it's an R by R square matrix that is diagonal, positive entries only, right, and non-singular as well, because it has no 0 values along the diagonal. All right, so we've now decomposed this as follows. So the next thing that we can notice, once we've got this decomposition as follows, or as we've just done, right, then we can write down the following, which is that A times V2, so A times the matrix of these values right here, these vectors, these eigenvectors correspond to the 0 eigenvalues, right, of A transpose A. And so therefore A times V2 is going to equal the 0 matrix. And this is because V2 form a basis, an orthonormal basis for the null space of A transpose A. All right, so since the columns of V2 forms a, in this case, orthonormal, right, basis for the null space N of A transpose A. So A times V2 is the 0 matrix. Similarly, we can write the following. Since V itself is orthogonal, remember this is the orthogonal diagonalizing matrix, right? So since V is orthogonal, then the following is true. V transpose times V is how we usually write, but also V times V transpose is equal to the identity matrix, right? And this is equal to, because it's orthogonal, because of the way everything's defined here, V times V1 transpose plus V2 times V2 transpose, so V1 times V1 transpose. And then what we can do is multiply this all by A and write the following. So A is equal to A times I, that's true, right? Which is equal to A times V1 transpose plus A times V2 transpose. But we just said that this portion is 0, right? That portion is 0, and so what we have here is that actually A itself is equal to A V1 transpose. All right. And so at this point, we have definitely constructed both of the matrices that we need, right? But we have this property here, and we're going to use this as we move forward. Okay, so at this point we're ready to start trying to find the matrix U. So what we need now is we need to construct the matrix U such that the following is true, right? Such that A is equal to U sigma V transpose. Another way to write this, though, is that A times V, if you multiply V on both sides, we know that this is orthogonal, so this will be the identity. So another way to write this is that A times V should equal U times sigma. And we're going to use this fact to help us compute this, because for the first R columns, we can write the following. Remember, we decomposed everything in terms of the non-zero eigenvalues of A transpose A and then the zero ones. So for the non-zero ones, for the first R, we have the following identity. We can say for sure that A times Vj, where j is just one of the indices between 1 and R, right? This is going to be equal to simply sigma j times the column of uj. Column of u, the jth column of u, the one that we want, right? But the point here is that we have our sigma j times uj. That's because this is a non-singular diagonal matrix, right? So multiplying this way just multiplies each column of u by sigma j. Recall also here, so this is for j equal to 1 through r, right? The sigma j's are not 0, so we can divide through, right? So since the sigma j's are not equal to 0, then we get a formula for our u sub j's automatically. So u sub j is then equal to 1 over sigma j times a times vj. All right? We can then put the following. We'll call this our matrix U1. We're going to write this as a partition matrix as well. But put that our matrix U1 equal to the columns U1 through UR that we've just defined by this formula right here. All right? And so just by construction here, then we have actually the A times V1 is equal to U1 times sigma 1. Okay? And actually, this is almost what we want, right? Because this tells us then that A is equal to U1 sigma 1 V1 transpose. And we'll see later that this is actually, for a lot of applications, this is what people actually use. This is called the condensed form, so the condensed SVD. It's not the full SVD. We're not done yet, right? We haven't found the rest of the columns of U yet. But this is the condensed SVD, and in many applications, this one is enough. All right, so one thing that you should do here, I didn't state anything about this yet, but one thing that you should do as a recommended exercise is verify that the columns of U1 are indeed orthonormal, right? Because to be an orthogonal matrix, all the columns need to be orthonormal. So that takes a little verification. It's not too hard. So just go through the process of verifying that those are orthonormal. Now, what about the rest of the columns of U? Notice that the way that these are defined, each of the columns of U so far that we've defined, U1 through UR, live in the column space of A, right? Because they're A times something. So they live in the column space of A. So let's write that down. But since each of the uj that we found so far are in the column space of A, right? This is for j equals 1 through r. Then the columns of U form and since they're orthonormal, which you're going to check right here, right? Then these columns of U are going to form an orthonormal basis for the column space of A because there are r of them. So they have the proper rank, right? It's got the full, it takes care of the full rank of the column space. All right, so this means then that the columns so far of U1, right? We call this U1. These form an orthonormal basis for the column space of A. Well, now if we remember our fundamental subspace theorem, so by the fundamental subspace theorem, remember that the range, or the column space, right? But the range of A transpose, or sorry, the perp. So the orthogonal complement. Sorry, that looks like a T. So the orthogonal complement of the column space is the null space of A transpose. So there's where the transpose comes in, right? And so this tells us exactly how to compute the remaining columns. We need an orthonormal basis for the null space of A transpose. All right, so the remaining columns of U are an orthonormal basis of the null space of A transpose. So that's how we compute those. So remember how you would do this. You would find a basis for the null space and then use Gram-Schmidt to make it orthonormal, right? So find any basis of the null space, then use the Gram-Schmidt method to get what we're going to call then our U R plus 1 through UM in this case. Remember, U is an M by M matrix. All right, and so at this point we're pretty much done, because now we put our U equal to the partition matrix U1, U2, and the SVD becomes, so again, this is what we want here, right? That's our last matrix that we were looking for. So the SVD of A is then given by, so A equal to U times sigma times V transpose, which in partition form is U1, U2 times the block matrix sigma 1, 0, 0, 0 times transpose of the partition matrix V. So that's going to be V1 transpose V2 transpose in a vertical form, right? And that all, if you work this all out, all that you're left with after all this is U1 sigma 1 V1 transpose, which is what we said before is the condensed form, right? But the full SVD is this form right here, this block matrix form. So after all that, that was, like I said, I warned you, it was going to be very long for the proof, but the proof is very, very useful in this case. Sometimes the proofs are a little abstract and you don't really know what's going on. This one, though, is extremely constructive in that it tells us exactly how to construct the SVD for our given matrix, right? So we started with a matrix A. What did we do? We computed A transpose A. We then diagonalized it, so we found its eigenvalues. We ordered them from largest to smallest, decreasing, and we found the diagonalizing matrix, right? So the matrix of the orthonormal columns, right? The orthonormal eigenvectors, basically. So basically, all you need to do is find because of the format here of A transpose A having orthogonal eigenvectors anyway, you just need to make sure that they're each unit vectors in your matrix V and that they're ordered in the same order as the decreasing eigenvalues, right? The singular values are then, so that's how you get the matrix V. The singular values are then the square roots of those eigenvalues, right? And they're all, once you've got those decreasing, the sigmas will also be decreasing because of the way the square root function works. So that's good. So then we have our matrix sigma. And then for the matrix U, we have a formula for the non-zero singular values. Probably should put a box around this one because this one's going to be important. We're going to use this one in our examples. So this is the formula for computing the columns of U that are that correspond to the singular values that are not zero, right? And then if there are any zero singular values, if there are any columns left over of U, then what we do is we just find a basis for the null space of A transpose, and from there you use Gram-Schmidt to make that basis orthonormal to find the rest of the columns. But this formula right here will give us orthonormal columns for the first R columns of U automatically. So it's a very useful formula. Okay, so the next step is to do a couple of examples. All right, so for our first example, this is item 3 now. The proof was so long I forgot what number we were on, but for number 3, let's just let's do this for a matrix that's not too crazy, because that whole process I know probably feels overwhelming right now. So let's start with just this matrix A that's given by 1, 1, 0, 1, 1, 0 for the two columns, and let's compute the singular value decomposition of this, just following all the steps that we've outlined in our proof. So remember, the first step is to compute the matrix A transpose A. So A transpose A is going to be the matrix 1, 1, 0, 1, 1, 0 as rows times the matrix with the same columns. It's got to be symmetric, and because the rows and columns are all the same, it's easy to compute this one. It's going to be 2, 2, 2, 2. And then remember, we need to compute the eigenvalues of this matrix, and those will be the squares of the singular values of our matrix A that we started with, right? So for A transpose A, the eigenvalues, we can compute these, right? So if we do A transpose A, I guess we'll call this item 2. I'm probably going to lose track of the count here. But A transpose A minus lambda I, this is going to be 2 minus lambda, 2, 2, 2 minus lambda. And then that determinant is going to be lambda minus 2 squared, because you can flip the sign, minus 4. And so that's lambda squared minus 4 lambda plus 4 minus 4, or just lambda times lambda minus 4. Setting that equal to 0, we see that lambda 1 is going to be 4. I'm going to do these in order, right? So the biggest one is 4, and then lambda 2 is going to be 0. So the two eigenvalues are 4 and 0. Again, order them bigger than smaller, right? So this then tells us what our singular values are. So our sigma 1 is going to be the square root of lambda 1. Square root of 4, which is 2. And sigma 2 is the square root of lambda 2, which is, of course, 0. And so this tells us that our sigma, we'll just do the whole decomposition here, but our sigma is going to be the matrix. It's got to be a 3 by 2, right? So it's going to be this matrix. So there's our matrix sigma. So diagonal entries are the singular values, 2 then 0, but it's got to be the same dimensions as A, right? So it's got to be the same size as A. So let's put a box around this one. We've got sigma. We need to find our U and our V. Remember, the V is built by it's the diagonalizing matrix, so it's the matrix of eigenvectors, corresponding eigenvectors of A transpose A, right? So we just use the eigenvectors of A transpose A, and we make sure that they're unit vectors. So they're going to be orthogonal by just because of the form of A transpose A, and then we'll make them orthonormal by making them unit vectors. So we'll call this item 3 now. So for item 3, we'll start with our lambda 1. So obviously lambda 2 is going to be the null space, but let's get them in order, right? So let me call this x1, and then we'll convert it to v1. So x1 is going to be solutions to the equation, right? So we're going to subtract the 4. We're going to do, here, I'll just write it this way. It's going to come from, it's a basis of the null space of A transpose A minus lambda 1I. All right, so here's what we're going to solve then. We do 2 minus lambda 1, so that's 2 minus 4. So negative 2, 2, 2, negative 2, augment it, find the null space. Well, as usual, in this case, these two rows are dependent, and then we can rewrite this whole thing by some simple row operations, right, as this. And then at this point, we can say, all right, well, these just have to be equal to each other. They have to be equal to each other. So our x1 can be anything, alpha times 1, 1. Right? Alpha, negative alpha plus alpha equals 0. That's going to solve this. And then we just need to make sure that this is a unit vector. So the length of this portion is square root 2. So our alpha has to be 1 over square root 2. Right? So our vector v1 is going to be 1 over root 2 times 1, 1. All right, so that's the first column. This is the first column of our matrix V. Now we need to do the same thing for the second column. Second column is actually just the null space of A transpose A because the second eigenvalue was 0. So the matrix A, remember, was 2, 2, 2, 2, right? All 2's. So we augment this. It's very similar, and I think you can probably, in your mind, see exactly where this is headed already. And so this one, our x2, is going to be alpha times. This time they have to have the opposite sign. So now you get a choice, right? So I didn't state this in the whole proof. It was already long enough. But the matrices U and V are not unique. There are different answers. It's okay. You can get different answers to those. But the matrix sigma is always going to be unique. So this matrix sigma, that's the only answer you can get for sigma. The matrix V, though, can be a little bit different, but whatever we choose for V, remember, it affects what we get for U. So the matrix U is built out of V in some sense, right? At least part of it. So that's why you can get different matrices, but still have the same, this same product when you multiply everything together. Anyway, so the point here is that either one of these can be negative. I'm going to do it this way. If you choose to do it the other way, it's fine, right? Nothing is wrong with that. And then the same deal, this alpha has to be root 2 again, or sorry, 1 over root 2 again to make sure that this is a unit vector. So our V2 is 1 over root 2, and in this case, I've chosen to make it 1, negative 1. You can do negative 1, 1 if you want. So we put this all together to write our matrix V. I'm going to factor out that 1 over root 2 since it's the same factor on each one of these. And then the matrix is 1, 1, 1, minus 1. That's orthogonal matrix right there. And so I'm going to put a box around this as well. All right, so there's the matrix V, the matrix sigma. So far, we've got those, right? Now we need to make the matrix U, so I'll call this item number 4. U1 we can get just by using the formula that I had highlighted up here in blue. So U1 can be done by this formula, right? So let's do it. So U1 is done by the formula 1 over sigma 1 times A times V1, right? So 1 over sigma 1. Sigma 1 was 2. A is our matrix that we started with, so 1, 1, 0, 1, 1, 0. And V1 is the first column here, right? So it's 1 over root 2. So we'll factor out these constants, but then times 1, 1, right, for V1. So as we factor this out, we get 1 over 2 root 2, and then we can do the matrix multiplication. We're going to have a vector that is a 3 by 1 here, right? So it's going to be 2 in the first slot, 2 in the second slot, 0 in the third slot. These 2's will cancel, right? 2, 2, 2, 2. This is a 0, so it doesn't matter. And we get 1 over root 2, 1, 1, 0. So it turns out to be just the column of A. Remember, the first column of A, well, the columns of A are the same, right? And scaled. And that's not a surprise. Remember, we said that the first column, the first few columns, the first R columns of U form an orthonormal basis for the column space of A. Well, look at A. A's columns are the same, right? And so obviously the column space is spanned by this 1, 1, 0. That's not a surprise. We just had to make it into a unit vector. And so we could have bypassed the whole formula. I wanted to use the formula because in general, using the formula is the easiest way to do it, right? But just by a little bit of thought before we did this, before we just went straight to the formula, we could have very easily found this vector U1, right, without doing all this work. But it's okay. There's nothing wrong with what we did, right? So the second vector, the second U2, this is going to have to be a unit vector basis of the null space, right? So an orthonormal basis of the null space of A, right? And so A is going to have a null space of dimension 2 because of the rank nullity theorem, right? So its rank is 1. It's going to have a null space of dimension 2. So let's try to find that then. So the null space of A, it's A transpose, sorry. It's right. The rest of these come from the null space of A transpose. Where did I write it? Null space of A transpose, right? The null space of A transpose. So null space of A transpose. So U2, this is really going to be U2 and U3, right? U2 and U3 are going to come from the null basis of the null space of A transpose. All right, so A transpose is 1, 1, 0, 0, 1, 1, 0, 0. So to get the null space, you augment it the usual way. Just like before, we've got, the rows are exactly the same. So this is, as far as solving a system, augmented matrix style, this is simple, right? So what do we have here then? Well, basically, the formula here is going to say that what? X1, if we call these just X1, X2, X3, X1 has to equal minus X2. X2 is free. And X3 can be anything, right? X3, yeah, it's free, right? X3 is free because 0 times X3 is 0. It doesn't matter, right? So X3 is free. Okay. So in this case, then, our basis is going to look like, so we're going to get, I'm going to call these X because we still have to make them unit vectors again, and we might have to do Gram-Schmidt. We're going to look at these and see what they look like, right? But they're going to look like the following. So it's going to be something like, I'll write this in 2 stages. So our free variables are alpha, X3 is alpha, X2 is beta, and then X1 has to be minus beta. And so this is going to be like alpha times 0, 0, 1 plus beta times negative 1, 1, 0. These are already orthogonal, these 2 columns. If you do the, this transpose times this, these are going to be orthogonal for sure, right? So they're orthogonal. We just need to make sure they're unit vectors. So we don't have to do Gram-Schmidt, luckily. This one's a unit vector, right? So we can just make that one be U2. U2 is going to be the vector 0, 0, 1. And then this one's not a unit vector, but it can easily be made one with a 1 over root 2, just like our other ones, right? So U3 is going to be 1 over root 2 times negative 1, 1, 0. All right, now we put this all together, and we're pretty much there, right? So this is our first column, second column, third column. If you factor out the 1 over root 2, then you just have to throw a root 2 on this one, right? So this whole thing can then be written as U is equal to 1 over root 2 times, and then the first column, 1, 1, 0. Second column, 0, 0, root 2. Third column, negative 1, 1, 0. All right, so there's the matrix U. And we're pretty much done then, right? So we've found all the parts. We found the sigma, we found the V, we found the U. The V transpose is going to be exactly the same as V, actually, for this one, right? So V transpose will be the same. And so what we found then is that A is equal to U sigma V transpose. It's going to be 1 over root 2 times 1, 1, 0, 0, 0, root 2, negative 1, 1, 0, times sigma. Sigma was the matrix 2, 0, 2, right? Everything else is 0. So 2, 0, 0, 0, 0, 0. And then 1 over root 2 times the 2 by 2 matrix V transpose. Transpose, though, is not going to change anything for this one. This one's symmetric. 1, 1, 1, minus 1. All right, and so there's the singular, that's the full, right? The full singular value decomposition of this matrix A. All right, now the singular value decomposition is very useful for many reasons, right? One thing is that it's very easy now to see the rank of the matrix, because the rank of the matrix is going to be the number of non-zero singular values, right? So you just look at this matrix in the middle, this sigma matrix, and you count the number of columns that have a non-zero entry, right? It's 1. So this is a rank 1 matrix. This matrix that we started with, remember, the matrix is, if you can check to multiply this all out, that it's going to be that, right? But this matrix was very easy to tell that it was rank 1, but it's still useful. Notice that this singular value decomposition, the singular values are in some sense like, they're not the same, but they're like they're related to, they're similar to eigenvalues for a matrix that's not square, right? This matrix is not square, yet the singular values kind of give us information similar to the eigenvalues of a square matrix. So A transpose A is always a square matrix. We found the singular values by taking the eigenvalues of that square matrix that's related to this one, right? Closely related to this one. So it's not a surprise that the eigenvalues, that the singular values behave kind of like eigenvalues, except they are definitely different, right? Because they're always going to be positive real numbers. They're always going to be positive real numbers. So even for a matrix that is square, the singular values do not coincide with the eigenvalues. So when I say that they're like them, I don't mean that they're the same, right? They are different. They are different, okay? But the point, though, is that they are single numbers which tell us something about the matrix as a whole, right? And how the matrix behaves. All right, so for the last example, I'd like to show you guys a slightly different method that takes advantage of the geometry of this situation. So this is number 4, right? So for this example, let's consider the matrix, and then we'll take a moment to just think about what the SVD is actually doing when it decomposes the matrix. But for the sake of this, let's write down the matrix first. So the matrix that I want to study in this one is going to be a little bit different than what we usually use. So this one's going to have decimal entries, so 0.4 and 0.9 in the first column, negative 0.3 and 1.2 in the second column. And so this is our matrix A. We want to try to find the singular value decomposition of this matrix. This matrix is a 2 by 2 matrix. So the way that we want to think about the SVD is as follows. Really, we want to think about the matrix A as mapping vectors from its row space to its column space. And then the matrices V and U are orthonormal bases of the row space and the column space respectively. So the columns of V form orthonormal bases of the row space of A, actually. And that's why there's a transpose here to turn them back into rows. And the columns of U form orthonormal bases for the column space of A, which we already talked about, right? That's exactly how we got U. We found, we considered, right, that the vectors U all lived in the column space of A. So here's how we're going to approach this then. So our matrix V, as we've already talked about, is an orthonormal basis for the row space of A, and then the vectors U are built out of those vectors V by mapping A, but they're supposed to be orthonormal basis for the column space. So all this is to say that when we do the SVD, what we're looking for to build our matrices U and V, we're looking for orthonormal bases of both the row space and the column space. So we're looking for, in this case, this is in R2, right? So we're looking for a pair of vectors. I'm just going to draw them maybe like this. So remember, they're unit vectors too, right? So a pair of unit vectors, this should be V to start with. So we're looking for our V1 and a V2 that form an orthonormal basis of R2, so pretend that's orthogonal, right? And then for which now, so there are lots of orthonormal bases for R2, right? But we want to find an orthonormal basis of R2 for which, after applying A to these vectors, we get two vectors that are orthonormal as well, right? So my angles are really bad here, but this could be pretty close to this one, right? That's not a straight line the way I've drawn it, but so the idea here is now this one is going to be if we have this basis, right, and the way A works here, but maybe this one is U1, which is equal to A times V1, and then this one would be U2, A times V2 potentially, right? And so this is the geometry of the situation. We need to find these vectors so that applying A preserves the orthonormal, right? The orthogonality at least, and then we can make them unit vectors if necessary. But we need to preserve the orthogonality of these basis vectors here. All right, so this is the idea. So how are we going to find these? Well, we've talked about how to find them in a purely matrix approach, But there's another way, especially in R2. If we're working in R2, then all of the possible vectors, right, are vectors whose terminal point lies on the unit circle. So we can consider the unit circle here. This is the set of all points for which x squared plus y squared equals 1, right, just the unit circle. And so these are all the vectors of length 1 in the usual norm, the 2 norm as we call it, right? And so then what are we going to do? We're going to look for two vectors that are perpendicular, right, or orthogonal on the unit circle here that map to orthogonal vectors. Okay, now they might not be unit vectors. We need to make these unit vectors. So up here I probably should put quotes here, because remember we have to actually scale this. We divide through by the singular value as well, right? But in the right, so these might not be unit vectors is the point. So the picture is going to look like this. We're looking for a vector that lies on the unit circle here, and then a vector that's orthogonal to it also lies on the unit circle. So this one we could say the components are cosine of theta and sine of theta. And then this one over here, its components would be, we did this when we studied rotation matrices, right? This one would be minus sine of theta and then cosine of theta. We worked this out in a previous lecture, way back toward the beginning of the course. You can work this out again, but these are the two vectors that we're looking for. And as we allow theta to vary, we can look at what happens to the image vectors, the u's, right? The image vectors, when we apply A to this matrix right here. So these are the two vectors that we're gonna start with, and then we're gonna rotate this around. We're gonna allow the theta to vary until we end up with two vectors, which again might not be unit vectors. So let's draw them as not unit vectors, right? Let's maybe they look something like this, but two vectors that are orthogonal for sure. So maybe it stretches like this, and that fixes the picture I drew up here, right? And so the idea here is that it doesn't matter. There could be some reflection happening here too. So maybe the image of this one is this vector, and the image of this one is this vector. We don't know. It depends on A. It all depends on A, right? Okay, so the point though is that we can, especially if you're doing this on a computer, you can use what's called some kind of variational method, where you assume that the vectors V are of this form, cosine theta, sine theta, and then minus sine theta, cosine theta, and then your job is just to find theta, or at least to find, you allow theta to vary, and then you carefully compute what theta has to be, or at least what cosine theta and sine theta have to be. That's what really matters, right? And then from there you get back, you've already applied A, right, to find the ones that are orthogonal, so you get back your singular value and your vector u in the process. So I'm not going to work this out entirely for this one, but what I will do is just give us the results as if we were going to do this, use this method on this matrix A here. So what we would find are the following. So if we use this, by the way, these are unit vectors, right? So we'll just have our v's if we go through this. But what we'll find is that our v1 and our v2 in this example for this matrix, it's totally dependent on this matrix, but for this matrix, but this geometry is important, right? So for this matrix A, we would get, you just multiply this through and you get an equation. So we would get that v1 is equal to, it's got to be a unit vector, right? So it's going to be 3/5 and then 4/5, or everything here is in decimal form, right? So in decimal form, this one's 0.6, 0.8, right? And v2, similarly, is going to be very, very similar, minus 0.8 and positive 0.6. I mean, once we know this one, you can, just by comparison, get this one, right? Because that's the way it's going to work for a 2x2 matrix. So I'm just giving us these. Now, how would you do this? Well, you would multiply through, you'd solve some equation, right? You'd try to find out, you would want, you don't just solve some equation, but you need to work both of these out, and then, right, with the cosine theta, sine theta, multiply it out, you get vectors in terms of theta, and then you take the inner product of the a v1 and a v2 and set it equal to 0, and then you'll get an equation for theta, And if nothing, you know, this theta is maybe not nice, but the answers are nice, right, for the cosine theta and the sine theta. So I'll leave the details of that as a recommended exercise, but you should at least write out the beginning of it, and then if necessary use a computer to solve the end of it. But let's make sure, let's just verify that these are definitely orthogonal, these two, because we started with them orthogonal. Let's verify that the image vectors are orthogonal, and then we'll determine what we have to do to find our u and our u1 and our u2, because our v1 and our v2 now we have, right? So we can just write down our matrix V. Our matrix V is going to be this one. It's a rotation matrix, actually, right? So there's our matrix V. It is orthogonal. We're good to go, right? So now we need to apply A to each of these to help us find the V. This is also going to give us our singular values. So the singular values deal with the stretching of these vectors, right? The dilation that you see in this picture. So AV1 is going to be this product. So the matrix A times our vector v1, which was 0.6, 0.8. And if you work this out, you will get, so this first one's 2.4 minus 2.4, that's 0. And the second one, if you work it out, you're going to get 1.5. All right, and so this is, to make this a unit vector, we have to factor out this 1.5, right? And then there's a unit vector. All right, and then if we do this for for v2, right, a times v2, we're going to see something very similar. By the way, if this is the basis vector u1, we can kind of guess what u2 is going to be, right? But let's do it. So the second one we're going to multiply by negative 0.8 and then positive 0.6 like this. This time, if we multiply this all out, we're going to get negative a half from the first multiplication, which you can check. And then we will get, in the second one, we'll get 0. Okay. And so this all works out to be if we factor this out again, right? Negative 1/2. Sorry. You don't want to factor out a negative, so I'll tell you why in a moment, but we want to leave the 0.5 here and then leave the negative here as part of our basis vector. All right. And the reason, though, here is because the reason that we want to do this is because now, once we have this decomposed as follows, then these are the singular values. Remember, the singular values have to be positive, right? And so we also got these in the right order. Now, when you work these out, you might have to change the order of your u1, your u2, your v1, your v2, because remember, the singular values have to go from largest to smallest. So this one's going to be our sigma 1. Whoops, that's the wrong tool here. This one's going to be our sigma 1, and this will be our sigma 2. And then what's left here, these vectors, these are the orthonormal basis of the column space. So this is our u1 and this is our u2. And so now, using everything that we've done, let's highlight our vectors v1 and v2. We've already got our matrix V, right? But using all this, we can then decompose our matrix into its SVD. So our matrix A is going to be equal to the matrix U. So that's this one. It's going to be 0, 1, negative 1, 0, times the matrix sigma. That's going to be 1.5, 0, 0, 0.5, times the matrix V transpose, right? V transpose. So that's going to be 0.6, 0.8 in the first row, negative 0.8, 0.6 in the second row. And you can work this out, but this will be equal to A. When you multiply it all out, you'll get back to matrix A, and therefore it must be the SVD, right? So this matrix U, this matrix V transpose, and really the matrix sigma here, that's the main one. These are the singular values, 1.5 and 0.5 of this matrix A, done slightly differently, so done by this geometric argument. Okay, it's usually going to be easier in computation for small matrices to do the way that we outlined in the proof, right? But this way, though, is geometrically significant, so it depends on the problem that you're trying to approach. But that you're trying to solve. Whether or not you want to do the geometric method, maybe the geometry is the whole point of the problem you're trying to solve, right? And so then this geometric method can give you more insight in some ways than the other method. But no matter what, no matter how you get your SVD, the geometry is there, right? It's there, no matter how you compute it. So I'm going to leave this here, and I'll talk to you guys in the next lecture.